So, last section from chapter 8 is about improper integrals. We would probably not complete this section today. Oh, that's interesting. There we go. I've got an interesting question. I've got this expression, area, which is a function of b. Now, the b variable is how far along the x-axis am I going to go? And then you're going to return to me the area from 0 to that value x equal b. Can you guys work in pairs, please, discover a simpler form to fill in that box, where that I simply can take the value b and plug it in, and you can tell me, so I don't have to do this integral over and over again. Those in the calculator. No, that's here from TI-89. So again, discover for me the expression with b so that I can find out how much area is from 0 to b. Surely there's not enough boxes.
Find out the area?
I mean, if b was 1, could you find the area from 0 to 1 for me? If b was 3, could you find out the area from 0 to 3 for me? Have you forgotten how to take the antiderivative of e to the negative x over 2?
Yes, I do. I am.
You have? I suppose I can do over here a little side work, where I take e to the negative x over 2 dx, and I would probably suggest a u substitution of negative x over 2, exactamundo. That's what I would probably do. Why is this useful? Well, if I ask you to do 5 problems, what's the area when b is equal to 1? What's the area when b is equal to 2? What's the area when b is equal to 3? What's the area when b is equal to 4? What's the area when b is equal to 5? If I ask you those 5 problems, would you rather have found a general solution once and then plug those values in for b 5 times? Or would you like to have done the integral 5 times?
The first one.
The first one. Okay. Let's see if what I wrote is right. Oh, look at that. What a surprise. Okay. Now, this is only the first step in what I want to introduce today. And that is, how much area is under that curve from 0 to infinity? I've got that curve. That curve has asymptotic behavior. It's getting closer and closer to the x-axis all the time. As I go infinitely that way, toward, what would that be? 9 Mile. Past 9 Mile. To 8 Mile. Further south. McNichols. Further south. All the way to Jefferson. Across the river. Now we're in Windsor. Well, after the river, we hit Windsor. After Windsor, we stay in Ontario for a little while, and then we hit Lake Erie. And swim across Lake Erie, and then you end up in Ohio.
I was skipping a lot.
Yeah.
Really?
I'm sorry? Okay, so the question then becomes, if I want to find out how much area is in that curve, not from 0 to 1 or 0 to 5, it's from 0 to infinity, then I can take that expression of area and I can take its limit. I can say, what is the limit as b approaches infinity? Looks like 0. I mean the little b that's it's in the drawing. Okay. Now, I think this is a surprising outcome. The limit as b approaches infinity of the area the area as a function of b is 2. Wait, we have a curve that goes on infinitely that never touches the x-axis, and yet there is a finite area underneath that curve.
What?
I think it is too. Now, the name of this section happens to be improper integrals. Let me explain why we say some of this stuff is improper. This idea, the area under this curve from 0 to infinity, could be written as the integral from 0 to infinity of e to the negative x over 2 dx. The presence of that infinity sign makes this an improper integral, because the limit of integration is not a number there, because infinity is not a number. It is a placeholder. Right? So what are we going to do when we encounter these improper integrals that stand for these very strange ideas, that area under the curve for an infinite amount of weight of going? Well, here's going to be our plan. That we are going to essentially do that kind of work. We are going to convert improper integrals into a combination of integrals and limits. And can you hear that? Okay, can I go to the next slide? No, Kelly's still writing. I'll wait for you, Kel. Tell me when you're ready, Maddie. Okay. All right. So here's what we're going to say. Here are the different kinds of improper integrals we're likely to encounter. One of them is the one I just displayed in the first problem, and that is an integral from a finite bound to an infinite bound, from a to infinity. And what I want you to do is when you see that kind of form, I want you to think of the infinity being replaced with some variable. Typically we use b, and we say it's the integral from a to b, but then we're going to take the limit as b approaches infinity. So we're breaking it into two parts, finding a general solution, going up to b, and then say what happens when b goes to infinity. Now it's also improper to have an infinity sign, or sorry, a negative infinity sign as the lower bound on an integration. As in the integral from negative infinity to b of f of x dx in the second point on this slide. When we encounter those, again, what are we going to do? We're going to replace the negative infinity with some variable, how about a, and then say, what's the limit as a approaches negative infinity of the integral from a to b? When we have infinities on both ends of a limits of integration, as in the integral from negative infinity to positive infinity, we're going to replace both of those with numbers. When we see that, we're going to declare some arbitrary point in the middle. Let's call it c. C can be any point from negative infinity to infinity. That gives you a lot of choices. And we're going to rewrite it as the integral from negative infinity to c plus the integral from c to positive infinity. And each of those in turn get replaced with limits as in step 1 and step 2 above. Infinities get replaced with limits is the theme of this slide. Are you ready to see this in action? Oh yeah. And let's do it, if you're ready. So, I want the derivative, sorry, the antiderivative, the integral from negative infinity to infinity of e to the x dx. How am I going to attack that problem? Well, is it improper to write this? So, what is it that they wanted you to do according to the third bullet point on that previous slide? We're going to change this from negative infinity to something, to c. Charlie, you get to choose the c, because Charlie starts with c.
11.
11. How about 11D?
No, because that's not real. That's
Actually, of all the numbers that you could choose, what would probably be the cleanest one to use?
0.
0.
I didn't choose 0 though.
I know, but I'm trying to. No one likes 11.
I like 11.
That's a great number.
You're just saying that.
No, it's not a lucky number.
We're kind of the class of 2001.
What?
We're kind of like the class of 2001.
Yeah.
Oh.
Yep.
There you go. Okay, now that we've broken it up that way, now what does the book want you to do? Now break these up again, where this first one is going to be the limit as a, can't make it a to save my life, from a, as a approaches negative infinity of the integral from a to 11 e to the x dx plus the limit as b approaches positive infinity from 11 to b of e to the x dx. So far so good? going to happen here? What is the antiderivative of e to the x? E to the x. E to the x evaluated from a to 11 plus the limit as b approaches infinity of e to the x evaluated from 11 to b. So now we're getting close to the end. Still can't write. A approaches negative infinity of e to the 11th minus e to the a plus the limit as b approaches infinity of e to the b minus e to the 11th. Now, here's where we introduce another new topic. When we have improper integrals, there are two possibilities. Those two possibilities, and tell me if you heard this before, is that they either converge or diverge. They converge if the limits exist. They diverge if the limits do not exist. So I want you to focus right here. And I'm going to ask you, does that limit exist? Does the limit exist as b approaches infinity of e to the b minus e to the 11? If it exists, it converges to a particular number, does it? No, because e to the power of infinity is really big. It's a really big infinity. E to the power of infinity is really big. We say that this limit does not exist. If this limit does not exist, that means that this integral diverges. And if this integral diverges, the integral from which it came also diverges.
And this would be like D and D, but it was like diverse. That's cool because it's like does not exist. It's divergent. Like up there.
Oh, my N's and my IV's look the same, don't they?
Yeah.
See if I can do this better.
No, I liked it because it helped me remember.
Okay. You can write it the sloppy way in your own notes. Oh wait, but you can't write sloppy in your notes. Alright, so do we have this new, okay, so these new expressions, these improper integrals either exist or they don't exist. When they don't, sorry, the improper integrals either converge or diverge. They converge when the limits that we use to evaluate them exist. They diverge when the limits we use to evaluate them don't exist. Alright. May I go to the next slide, please? I got one thumbs up. The rest of you are like, I'm on the ride. You just take me where you want to go. Let's look at another problem. With partners, please. This is 1 to infinity. The integral from 1 to infinity of dx over x.
Yeah, I rewrite it.
I'm not sure if I said that to you both right.
should I write next? What should I write next?
Limit of b to infinity,
As b approaches infinity of
1 to b. Dx over x.
you matching?
Yeah. I'm looking at this thing like that. Like that's a lot of It's just
So then from so now I solve the integral.
Oh yeah. Now watch out for that. That's the one that doesn't follow the power rule.
What does it follow from?
The antiderivative of e to the or x to the negative 1. You know, for most of the ones that look like this, it ends up, you know, you add 1 to the exponent, divide by that. But this is the one that doesn't follow that rule. So it's a natural log. Now what? Explain yourself, Chris. Chris thinks this goes to infinity. Marissa? You gave a little head nod.
It's like we tried it on the calculator. We put in a really big number and it just
Keeps on going up. As b gets bigger, the natural log of that number gets bigger. It does very slowly. I mean, the natural log of a billion is like something like 15. But as b gets larger, natural log gets indeed larger. So wait, so if that's true, therefore, the integral from 1 to infinity of dx over x diverges. It doesn't have a finite value. Now this is interesting. So in the first example, the e to the power of negative x over 2, it goes to infinity and has a finite area, 2. This is another one. 1 over x has asymptotic behavior to the x-axis. We're going for an infinite distance, and it has an infinite amount of area. Go figure.
divergence.
I think I meant to say that it has diverguosity. It's the hazard of being taught by a dyslexic. There we go. Is that better? D-I-V-E. Okay. Okay. So some of these functions, again, that have asymptotic behavior towards the x-axis, some of them have a finite area and converge to a value. Some of them are divergent. All right? One more problem of this type. I'm thinking of a two-word phrase. the volts. Again, lots of talking, please.
So that if unit goes from 0 to oh wait, we don't want that. Okay, so we need some sizing.
That helps.
So put in the
Yes,
building
there's
that
just
is
What?
I don't know. It's super weird.
what?
Do you like
I just try again. I can't remember the persuasion, which one's which. So I had to look at the inputs. Like,
Some
oh
of
yeah.
them have the same characters and we're choosing the
do
same.
you like the function of how to say put in a comment?
I would do the partial fraction decomp.
Close versus
Do it on the side, and then
all in one,
and
right?
do the whole. Then end up rewriting it. Can you rewrite it with the limit first? I would say you could probably rewrite it with the limit first because it's only one step and it's the part that you actually probably feel most secure about. By the way, not only are you going to do a partial fraction decomp, but I'm also going to ask you to start thinking about this question. By just looking at it, do you think you can figure out whether it converges or diverges?
Oh, well,
And that's a really good question. What would it take?
it converges to 0.
Okay, I know but
Well, wait, no, hold on. Hold on.
1 over x goes to 0, and it was not convergent.
Yeah, no, that's right.
How many people are going to get this partial fraction decomp done before I get it done?
No, you're not.
Oh, dang it.
I got 4 and I got 1. Oh, right. And then I said,
Did you get that?
oh.
Why is it? Wait.
Wait, oops. Once you get your decomposed fractions,
Like,
do you use them both separately and then? Okay. Yeah, no. Just face. I think you do. Otherwise, why would you decompose them? Because you put it back together and you get restarted. Why am I having a motion? Don't you mean A equals what you have? X together? Oh, when X is, oh, I gotcha. Yep. Okay. I gave away the answer. Okay, so we go like this. Right? Yeah, that's what I was thinking. Okay. So now we have.
I'm not sure.
Oh, okay. And then we do name.
Are you moving ahead of me? You're agreeing with me. You moving ahead?
We hit like a wall.
Okay. you start steaming ahead of me now?
Now do we evaluate?
What do you mean by evaluate?
Like some
Evaluate the limit, or we're talking about
The
evaluating the antiderivative?
Yeah.
Why?
Okay, I like the idea of the antiderivative.
Oh, so then isn't it,
Negative x plus 3
over x
or
plus
negative
3?
negative
This is that.
and
It can't be because that one's negative. It has to be
divide
yeah. So it puts its minus 1
over x.
Did I hear someone say divide?
Yeah. Brainstorming in this corner is happening.
I love dividing.
Alright, let's go.
X plus 3 over x plus 3.
What do you do with the negative?
What do I do with the negative?
That's
Well,
why it's
when you add two natural logs together, you can take the stuff that's inside the natural logs and divide one by the other. The positive one on top and the negative one on the bottom. When you have two positive ones, you can
Oh, we forgot to keep
multiply them.
Don't we?
so you do 0 and then
The 0 is
so and you have 1.
Would it just be ln of 1? Because whether you, when you plug in infinity for b, infinity plus 1 is the same thing as infinity plus 3.
So as if we're going to infinity, this
Yeah.
thing, this looks like a big
0
1,
or 1.
and the natural log of that,
That's
the natural log of that 1 is going to end up being just a big 0. So what are we left with?
0.
Negative ln of 1/3.
That,
Which most people would rewrite, by the way.
Oh.
Oh.
Now, I didn't know the answer was going to be natural log of 3. But I did know this was going to be a convergent interval. Yeah.
I don't know how. I'm more confused on when you did the b and the 0 part.
Going from here to here?
Yes.
Okay. So, after we found that antiderivative, and after I cleaned it up algebraically, are we okay with the clean up algebraically?
Yes.
Alright, so after I did that, I'm saying, oh, I'm going to evaluate that antiderivative at the top bound minus evaluating it at the lower bound. So here is me taking the upper bound, and every place I saw an x, I put a b. Minus
Oh.
me taking the lower bound, putting it in, and getting minus natural log of 1/3. Alright, it did take a long time. But you know, when you have a hard time remembering partial fraction decomp, that happens. Now, I want to tell you why I knew this was going to be a convergent. Right there. that x squared is enough to make it convergent. Let's see in one of the future slides, I don't think it's the next one, it's the one, we got one more to do, and then we're going to look at a general way of looking at particular integrals and determining whether they are convergent or divergent by inspection. But this is one more good practice. Oh, I'm thinking of a 3-word expression.
By parts.
Integration by parts. Or you could do this, by the way, using tabular integration. Either method is acceptable to me. Go.
Bad at writing extensions.
What's that, Charlie?
Terrible at writing extensions.
So isn't that the way you have AU and PG?
I didn't know that my son making his scores wrong.
How does he make them?
Yeah. See if E is negative x and
Yeah.
x, which gives.
My son makes his scores like this.
And then you have x.
Which then turns into
Just like, it looks like,
You know what really funny is? I mean, now it's like, no, make the thing and then do that, or make this and then go like that. And then I realize when I get in a really big hurry, I do exactly the same thing he does. He's so doomed. But that's all my
I wanna see what's in there.
Yeah. So get 1 minus
Okay, I got one step done for you. Like Mr. Fedor. Wasting my time. No, I haven't. All I did was put the limit in front. We know that's improper. We know that at the very least we need to do that. I use tabular. Did you want me to do it using integration by parts and using the V's too? This one lends itself to tabular.
So this is negative x equals negative x. Oh. Minus e to negative x.
And integrate the other side. Okay, we're less than 3 minutes. I better hop in here and help you guys out. think?
Conversion.
Okay, to what?
1 plus 2 over e.
Okay, I'm seeing this part here as being 2e to the negative 1. I want to know what's going on with this part here as b approaches infinity.
Well, what I did is, I took out, like, an e to the negative b. So then I had negative b minus 1. And then I
Oh, okay. Let me do that for everyone so they can see it too, Anthony.
So then I dropped all of the e's into the denominator. And when you have if you have negative infinity minus 1, that's still really large and really close to infinity, and e to infinity is really large and close to infinity, so I just took it as infinity over infinity.
Which is an indeterminate form in which L'Hopital's rule could be used. And if we apply L'Hopital, the b is going to go away, but the e to the b is going to stay. This bad boy goes to 0.
And then I get 2 over
2 over e is correct. And therefore that improper integral converges. We will finish this lecture tomorrow. I'll leave it up for a while. What's that?
I got scooped and I don't forget how we finished that.
Okay, we'll talk about tomorrow.